Hi everyone, welcome you all in another session of AI/ML. Today we are going ahead to understand about divisive clustering, like how they are actually working. Then we'll proceed to PCA, and then finally we'll move into some of the minor details that we need to understand that we will be covering up. Okay, so before that, let me just open my Excel file. Okay, fine. So let me just share my screen first. Okay. Yeah. Hopefully my screen is visible to you people and you are able to see my screen. So now we are going ahead to discuss in details about the divisive clustering. Okay. So let me just write it down. Divisive clustering. Okay, so how does divisive clustering actually works? Okay, that we need to find out. So divisive clustering is the opposite of agglomerative hierarchical clustering. About agglomerative hierarchical clustering, we have understood in details in the last session. Any one of you here not able to recollect, just go ahead and refer to the last session where we have just in details collected about the agglomerative hierarchical clustering. Okay. Now, what is this divisive clustering? Okay. Now you can imagine that you have a box of animals, okay? Animals like cat, dog, tiger, lion, rabbit, okay? So what happens here, agglomeratives start with each animal alone and combine them step by step, as we have seen in the last session, okay? Now coming down to divisive, divisive does exactly the opposite. It starts with all animal together, then it split them step by step based on the requirement and based on the usage. Okay, so that comes down to the divisive part. Okay, now how divisive clustering works? Okay, so for that we have taken this data set. So we have taken this example where we have got the six students and their scores in maths and science. Okay, so we want to cluster them using divisive clustering. Okay, now one by one, we will go ahead and see what are the steps that are required and eventually we'll follow each of the steps to do the divisive clustering. Okay, so going ahead, the first step, so step one, that is like starting with all points in one cluster. Okay, starting with one point in one cluster. Okay, one point in one cluster. Let me just increase the size. Yes, fine. So what we are doing, so the initial cluster that I'll be taking, so initial cluster, so it will contain all of the six students. So it will contain A, B, C, D, E, and F, all of them together. Okay, now think it of like all students standing together in one big group. So that is the formation of an initial cluster. Okay, now we need to find out the most different point. We need to measure the distance between all points. So here also we will be taking care with the Euclidean distance and we'll find 2 points that are farthest. Okay, so we will just help that will just help us to split it accordingly. Okay, so here we have got the different ones. So for A, it is 90, comma 85, 92, comma 80, 40, comma 45, 38, comma 50, 85, comma 80, and 42, comma 48, like that. Okay, so we'll check with A from B, A to C, then all of this pairwise measurement we need to do. Okay, So now I'll just give you the idea. I guess in the last session when we have gone for the agglomerator, in details I have explained you how we can create, like how to calculate this distance. Okay. Now we will take a distance roughly so that I can just give you the idea what are the parts. Okay. Now suppose for an example, A and C we are taking. Okay, sorry. A and C we are taking, that are the far points. Okay, and the distance between them maybe we are taking it around suppose 64. Okay, let's take it for B and D. So their distance is around suppose 61, and suppose let's take A and D. So this is 62. Okay, so this all you need to calculate using the Euclidean distance. How to calculate it? What are the points that you already get from the data set, right? So this point the 2D point of A will be 90, 85. The point for B would be 92, 80. The point for C would be 40, 45. The point for D would be 38, 50. The point for E would be 85, 80, and the point for F would be 42, 48. So this will be the points. And now as we have calculated the distance, the same way we need to calculate the distance. Okay. Now suppose I am just giving you the reference, like the far points are coming out around 64, 61, and 62. So the most different pair from this is coming out as A and C because they are far. The difference between them or the distance between them are far, right? So they are the most different pair. Okay. Now again, that is the step 2 to find out the most different pair. So let me write it for you. Step 2. So it would be to measure the difference between all points using the Euclidean, and then we need to find the 2 points that are farthest apart. So the work is to find the most different points. Okay, so that is we will be finding. Now going down to step 3. So after we have find out A and C. The most different pair is A and C. So this is the conclusion from this step 2. Okay, so this is the one. Now coming down to step 3, that is we need to assign the remaining point to the closest. Okay, so that we need to do it. So we need to assign remaining points to closest. Okay, so basically here the cluster 1 have a seed that is A, and the cluster 2 has another seed that is C. Because we have got the most different pairs than A and C, so we will be getting cluster 1. It is cluster 1 seed is A, and cluster 2 seed that is B. Okay, so this, sorry, not B, it is C. Sorry, we have find out A and C. Now we need to assign others based on which seed they are closest to. Okay, suppose I am taking B. Like this, you need to find out using the distance only. I am just giving you the idea. Okay, so B, so we are getting closer to A. So it is cluster 1. Now we are taking suppose D, that is closer to C. So that means it is cluster 2. We will be having E, sorry, that is suppose closer to A again. So it is coming under cluster 1. Next again, we have F, that is closer to C. So that is cluster 2. So this is how things are moving. So after splitting, we are getting for the cluster 1, we are having A, we are having B, and we are having E. Okay. Coming down to cluster 2, so here we are basically having C, D, E. Right? So this is how it is happening. Now we need to repeat for each of the clusters. So now we will be checking if the clusters are too big or have very different points inside. Okay. So if yes, then we'll split again using the same method. So we'll find the most distant point and then again assign. So cluster 1 contains A, B and E, right? So the most distance is A and C. So we'll wait. C is not here, right? Then A and B is the distance. Their distance is suppose small. So among A and B, we are checking. A and B, we are checking. So the distance is suppose coming out to be 5, the closest one. Okay. So, and we are checking for the distance A and E, right? So A and E, the distance is coming out suppose 7. So still similar, but we can't do the further splitting over there, right? So same goes down for cluster 2. Cluster 2 like C. Cluster 2 that is we are getting here C, D and F. Right? So all of it we are getting up here. Now the most distance is C and F and the closest enough, like we are getting to stop the split up here. Like the same we did in case of A, B and E. Right? So here we have worked with A, B and E. The same thing will be happen here. So cluster 1 will have the higher score and cluster 2 will have the lower score, right? Because suppose most distance we are getting in C and F and the close ever that is the stop. Since we are getting the close ever, will be stopping the splitting up there. Okay, so this is how it will be coming. So now if we are have to just take the dendrogram representation. So we'll have all students. Next, we'll have the two branches. So let's take here the shape like this. And this one is, again, we need to check this. So we'll just copy it here. So we'll just take it here. And for this, we'll just do it here. So here it will be high score and this would be the low score. Okay, and here we will be having the further division. So we will be having A, B, E, E, and for here we will be having C, D, and F. Okay, so for that, let's take an insert. Okay, we'll take it like that. This one, again, this one, here to here. Again, this one, here to here. So Here, I am unable to just share you how exactly the dendrograms will come up. But basically, if I need to just give you an idea, this is how my data, like my form will be going. Okay. So I have, wait a minute, let me check here. Mhm. Yeah. So here, basically, you can see this is how a dendrogram actually looks. Okay, so here is a dendrogram, is a tree that actually shows how cluster merge step by step. Here we have got A and B, there is some similarity. So we have merged A and B together. E and F then merged together. Then with E and F, we have got similarity with D. So we have merged D with E and F. And then we have got C similar to DEF. That's why C has been merged with DEF. And finally, we have got AB, some kind of we have to take accordingly from each, we need to form a group. Like that is the case of agglomerative, right? So from each, we have taken it like that. So the whole group has been formed. So here you can see that for agglomerative, we have initially started with single alone one, that is, it is coming from bottom up agglomerative. So singular way we have checked for each. So B and C were closer, so we have merged them together. So it formed B and C, and A were left out. So accordingly, we have formed a group as ABC. Going down for divisive, we have started from this group, and as we have found out, A and C are distant, so they would be from different group. So this is how they have formed different groups, and accordingly we have checked for A, B, E and C, D, E. The similar way they have checked, and there would be further sub classification that is going up here. So here we have got only four. That's why it has taken like from D, E, F, G. It has got the closest as D, E, and F, G. Then we have like the most distance coming down as D, E, and F, G. There is the distance, and accordingly we have separated each one of them. Okay, so that is the part. So we have to start with all together. Then we'll need to split into two big clusters, like as we have clustered it as D, E, and F, G, and then we need to split it further how it is needed. Okay, so that is the entire concept of dendrogram. Dendrogram in divisive. Okay, so divisive clustering, as I mentioned, start with all animals together and split them like step by step. So initially we have taken started with all points in one cluster, so we'll think all students standing together, then we'll find the most different point, that is the measuring the distance between all point using the Euclidean distance. Then we'll find the 2 points that are farthest apart. Okay, so this will help us to split the cluster. Then we need to assign the point to closest SID. So, like for A, which one is closer, for C, which one is closer, that we have seen, and accordingly we have just clustered them. Like here we have find like B is closer to A, D is closer to C, E is closer to A, and F is closer to C. So after splitting, we have got two clusters, A, B, E, and C, D, F, right? So here the same thing is happening from here. Just think like, let me just draw it up. So suppose we have A, B, C, D, E, F all together. Okay. Now from there we are starting. So if we are starting from there, like, okay, let's take it here. So A, B, C, D, E, F started from here. Now we have got two specific cluster. So cluster one coming down as A, B, E, and cluster two coming down as C, D, F. Okay. This is how we have done the first clustering. Now we have to repeat it for each of the clusters. Now we have to see, now we have to check if clusters are too big or have the different points inside. Like we can do the further classification of like further subdividing them, and because till now we haven't got the point that they are like all are single. That range hasn't came yet, right? So then also we need to just go on doing it in that form. Okay, so that is the main case that we have to do it up here. So basically, as I mentioned, devices start with all students or everyone together, then split them into smaller groups based on how different they are. Then we have to keep splitting until the groups are just right. That is the thing that we need to go on. Okay. So hierarchical clustering contains both agglomerative and divisive. So it is like finding similarities step by step, but one goes bottom up and another goes top down. Okay, so this is the main part about it. Now we will be going ahead and discussing. Hopefully things are clear to you. Now we will be going ahead and discussing about PCA. So what is PCA? So you imagine that you have a box of color pencils, okay, and lot of different colors you have got. So you want to organize them so it's easy to carry and use, okay. So now you notice that some colors are supposed similar, very similar, like light blue and sky blue. So instead of keeping both separately, you can combine them into one blue group without losing much of the information. That is the exact thing what PCA does. Okay, it reduces the number of dimensions, that is features, while keeping most of the information intact. Okay, so in simple words, if I need to give you an idea, so PCA is just like a organizer. You are well aware of the organizer nowadays. We use organizer to organize our things, maybe our books, maybe any of the jewelry items, maybe any of the clothes, whatever we are wearing, so that we are doing and organizing. So it find the most important directions in your data. This PCA, okay. So and it also helps you to see the pattern clearly without too much of the cluttered. So this is the data we have taken. So we have taken a table that contains this five columns, that is the features. So we have five features that are student, maths as a subject, next science as a subject, English as a subject, history as a subject, and arts as a subject. Now some subjects are similar, like maths and science. Right, because we maths and science go hand in hand, right? So PCA can combine similar columns into a principal component. Fewer columns would be there and easier to visualize and analyze, right? So that is the major thing. So you will be thinking about drawing one piece of paper. So you can draw a 3D object like a cube or a 2D in paper, right? So the 3D cube onto 2D, like you, if you are just project like the 3D cube onto the 2D, it sees it clearly, right? That is the exact thing that happens, right? So PCA is like projecting the higher dimensional data into fewer dimensional while keeping the shape intact. Okay, so this is what we are having now. Suppose mathematics and science would be combined. Like let's have a small data set. So let's just take this data, control C, control V. Now let's add another. We'll add D as well. So here we can keep it as 60, 65 like that. Okay, now we want to reduce two features, maths and science, into one feature using PCA. Because why we have taken maths and science? Because your maths and science are very similar. That's why we have taken it. Okay, so now we need to organize the data. That is the step one. Okay, this is PCA. PCA is Principal Component Analysis. Okay, the full form of PCA is Principal Component Analysis. Okay, So now going here, we'll go down to step 1. Okay, just a moment. Yeah. So the step 1, what I need to do here, so I need to organize the data. So this data I need to organize. So I'll be doing organizing the data. Okay. So organizing the data. So how we need to do it? So we'll just take X and as a variable. Okay. So we'll take X and here we will be just taking 90, 85. Then we have 70, 75, 70, 75. Then we have 95, 90, 95, 90. And then we have this 60, 65. Okay. Like this, we have the data. So we'll just add a shape over here. So we'll just, because this, at the end, these are the matrix. So we just need to take it. And this one. So this is, so X equal to, we will be getting this, okay, this matrix. Now we need to subtract the mean accordingly. Like what would be the mean that we need to find out? Then we need to just take it accordingly. We need to calculate the average for each of the column. Like this is one column, this is another column, okay. So accordingly, we need to just calculate the mean. So we are calculating. So these are the maths and these are the science. So we will be taking average and we will be just taking this with this and controlling the stuff. So we have got the value as 78.75. So this is the mean of maths, mean of maths. Okay. So that is how my values are coming. Now here I need to again do the average and we will be considering this with this and we'll hit enter. So here also the values are coming same. So we will be taking mean. This mean is of science. Okay. So this mean is of science. Now from each we have to just subtract the mean. Okay. So now just calculating it accordingly. So we'll take as math mean maths minus mean that we need to do and here we need to do science minus mean. Okay. So basically we need to do 90 minus 78.75, 70 minus 78.75, 95 minus 78.75. This is how we need to go. Okay. So for math, 90 minus 78.75 is 75 gives us 11.25. Okay. So 70 minus 78.75 gives us minus 8.75. Now 95 minus 78.75 that is giving us 16.25. And here 60 minus 78.75 that gives us minus 18.75. Right? The same way we need to do it for science. 85 minus 78.75 that is giving us 6.25. Now for here 75 minus 78.75 that is minus 3.75. For this 90 minus 78.75 that is coming around 11.25. And this one coming 65 minus 78.75 that is coming around minus 13.75. Right? So now this actually helps in centering, helps PCA to focus on different, not on the absolute value. Okay. So the difference is also needed, that is the minus part. Okay. Now we have to calculate the covariance. So how we have to calculate the covariance? So here the next step 3. So before that, step 1, we have to subtract, that is basically subtracting the value with mean, subtract the mean. Okay, that we have already done. Now we have to take the step 3. That is basically we need to calculate the covariance matrix. Okay, so we have got a formula, that is covariance of x and y, that is summation of x minus x bar, y minus y bar divided by n minus 1. That is the formula of covariance. So we'll get the covariance, like after calculating it, the covariance we will be getting, the covariance matrix that we will be getting, that is 218.75 and 137.5, and here we will be getting 137.5 and 87.5. Okay, so basically what is this x minus x bar? X coming down to maths, like maths marks, and x bar is the mean of the maths that we need to do, with y, that is science minus marks of the mean of science divided by n minus 1, the total count minus 1, that we need to do. Okay, after this is the covariance matrix. Next we need to find out, like the step 4, that we need to find out, calculate the eigenvector and the eigenvalues. Okay, this all we need to do. So after that, after doing this, we have to choose the principal component. So we'll choose the top eigenvector with the largest eigenvalue that keeps the most of the information. Okay, so that we need to do. So we'll do the step 5, that is basically choosing the principal component. PC means principal component. So we'll, as discussed, we'll choose the top eigenvector with the largest eigenvalue. So we want that 1D instead of 2D. So we'll pick the first eigen. Okay. So that is what we will be doing. Next, we have to project the data into this principal component. So we have this PC1. So we will be just projecting this values to this eigenvector. Okay. So now the 2D data will be reduced to 1D. Okay. So that is how we will be getting. So after all of this, like after step 6, that is the final step, that is we need to project data onto principal component. Okay. So that is the final task. So basically, if we have, suppose the student, we have student with maths and science marks, right? So basically this is 2D space. Now it will be converted to 1D, that is PC1. Here we will get one value. So suppose we have got value A, B, C, D, the name of the students. Now here we'll get some of the values. So we'll get the PC So we'll get the PC values accordingly. Like the suppose we have got the eigenvalue like this, like the PC1 value like 12.75. Like just for a reference, I am telling. So the same way we need to just take it all, like all of the values should be taken for B, and we need to calculate the values. Okay, so that we need to do for B, C, D, all of them. Okay, so now this, like from there we have got a, like we'll get a value. Suppose we got it for 5.87. For this we have got 9 point or 19.75, like that. 19.75. And for this we have got, suppose the value as minus 23.25. Like that we have got the values. So you can see like these are the like the assumptions values, that they are not the correct value. So you can see from here, like from here, we have got down to here, right? So there is no major loss of the data. We have just reduced the dimension from 2D to 1D. Okay. So these are the structures of PCA. So step by step, we need to organize the data as a matrix. Then we need to subtract the mean so that we get the center. We get the center of the data actually. Then we have to calculate the covariance matrix. Then we need to find the eigenvector and eigenvalue. Then we need to pick the top eigenvector with the with the greatest eigenvalue, that is the my principal component that I'll be choosing. Okay. Then we will be just going ahead and will project the data that we are having onto the principal component to reduce the data. Okay. So this is the main idea that we need to do. So PCA is basically used for dimensionality reduction. It keeps most of the information intact and makes the data easier to visualize and analyze. Okay. So we need to use the maths with mean, covariance, eigen, all accordingly with the maths and the science mark basically for this example, and with to work with numbers basically here. Okay, so these are the sections that we have discussed about PCA. Hopefully things are clear to you. So another we have the idea about TSNE. Okay, so what is TSNE trying to solve? So imagine the situation that you have, suppose 100 toys, okay? Each toy has many details like height, weight, color, softness, shape, and size. So that means that the toy live in the higher dimension. So you put your eye that can only see it to a 2D or 3D. 2D on a paper and 3D on a real world, right? So now how we will draw this toy on paper so that the similar toy stays together. That is the case that we are solving using TSNE. So what is TSNE? TSNE is another smart way of drawing complicated data on a 2D space while keeping the similar things closer to each other. Okay, so or even simpler. So TSNE is a we can think of is a magical map maker, we can call, that places the closer friends together and strangers apart. That is the idea of TSNE. So we need to give an idea what are the difference between PCA and TSNE. So PCA actually tries to keep overall the shape. What is the shape that my data set contains? It tries to keep the overall shape. But what happens going down to TSNE, it tries to keep the neighbors together. Whatever be the neighbors they are, it tries to keep them together. And PCA is a linear conversion, that is the straight line form. But TSNE is non-linear. It is curves and bends are there, and basically, PCA is good for compression, but TSNE is basically for best visualization. Okay. So, and of course, PCA uses the average. So, we have used the mean basically in PCA, but TSNE uses the probability. Okay. In a bigger idea about TSNE, so if we have the original big world, so many dimensions are there. So students have many features. Okay, so we calculate how close each student is to others. That is the part that we are doing using TSNE. And if we are having, suppose there is another one that is world 2, that is small drawing world, that is 2D. So we place dots on paper, we adjust the dots so that the closeness we can feel the same. Okay, if 2 points are close before, then we keep them closer accordingly. Okay, so basically, we will discuss about the steps of TSNE. So we need to measure the closeness in the bigger world, like including all of it that we need to do. We need to convert the distance into the probability. Okay, so first we need to measure the closeness. Okay, then step two coming down, we need to convert the distance into probability. Okay, then we will put the random dots on paper. Okay, that is the 2D. Now we'll measure the closeness in 2D. Okay, so basically here we are using for measuring the closeness in 2D. Basically, what we are calculating. So this is the distance that two dots are neighbor on the points or the paper that we need to put it. But here TSNE actually uses the T distribution. Okay, so why we are using T distribution? Because it keeps far points really far and it avoids the overcrowding and actually it spread the clusters nicely. That's why we are using the T distribution. And after that, we have to compare the both the ones. Okay, so that is the major part we need to do. We need to compare it and then finally we need to fix the mistake and then we need to stop when the figure wise or the visualization looks good. Okay, okay, so that is the part that we need to do it. We will be stopping when the visualization will look good. Okay, so these are the things that we need to do up here. Okay, so this is the part about going down about TSNE. Okay, so TSNE is this part. Now we have to discuss about hyperparameter tuning. What is hyperparameter tuning? Okay, so what is parameter? So imagine that you are learning to throw a ball. Okay, so now things that change by learning, that is how strong you throw and how accurately you can do that. Okay, so these are the parameters. So that actually change all of the details that we are going to. So that comes under like that comes under parameter. So hopefully you have got like what this parameter is all about. Now hyperparameter tuning is like just getting the data like suppose when we are working, okay, in some case like suppose we are doing the k means, okay, now we have evaluated our data and once we have evaluated our data like in the evaluation section suppose we have done the accuracy, okay, now we haven't got the accuracy in a proper way. What is the what my accuracy needs to be? Suppose I need at least 60% of the accuracy, but it is giving me around 30%. My model is giving me around 30% of accuracy. In that case, I need to backtrack myself and change something in the model, or like update the weights in the model so that it can just take it accordingly. Okay, so they this are comes this actually comes under this parameter section. Okay, so this exactly comes under this parameter section. So we need to understand this section well, and based on this we need to take it. Okay, so this is what we have discussed. So these are the parameters. So what is now coming down to the hyperparameter? So what is hyperparameter? Now suppose you have imagined, that is, before throwing you have to decide which ball to use, a tennis ball or a cricket ball, or how far the target is, how many practice throws you will do. So these are the things that needs to be taken. So this decision are made before the learning starts. Okay, so this comes under hyperparameter. So the very simple rule, that is, parameters is like learning automatically, and hyperparameters are chosen by humans. So we have to update the hyperparameters that we as a humans are choosing to make the difference in the model or the accuracy of the model. Okay, so why do we need this hyperparameter? Okay, so suppose, imagine, that is, you are baking a cake. So the ingredients that you use are flour, sugar, milk, all of it. Now the settings of the oven. Okay, so the oven temperature, the baking time, the quantity of the sugar or the quality of the sugar, that also matters. So wrong setting of the oven temperature will make you a bad cake, and right setting will give you a delicious cake. Right? So this hyperparameter tuning is equal to finding the best setting. That is the exact thing. Okay. Now machine learning example, if I need to give you. So let's say you have trained a robot based on student grading system. Okay. Now before training, you choose that how fast it will learn, and how complex it is, and how much or how many time it studies. Okay, so that specification you have given. Now, this choice greatly affects the result that the model will be giving or the robot will be giving, right? So that needs to be taken accordingly. Suppose we have KNN classification. So here my hyperparameter is K, the number of neighbors that we are choosing. In decision tree, the depth of the tree, like how depth I want my tree to be, like how tall the tree can grow. That is the update, right? So that is I wanted. About random forest, the trees, the number of trees I will be adding. In neural network, we have the learning rate. In SVM, we have the C, like how strict the boundaries is. In TSNE, the perplexity, that is how many neighbors to focus on. That is the point that we as humans are choosing, right? This are all are the hyperparameters. So we need to take a closer look into it. Now, what happens if these hyperparameters are bad? Okay, so suppose example, I am taking learning rate. Okay, so thinking, suppose we are making a learning rate too small. In that case, the learning will be very slow. And if we are taking too big, then it will jump off and pass the some part of it. Okay, so we need to take just right, like just the exact right learning rate. We can't take it too small, can't take it too big. Okay, too small learning, actually it tells that it will never learn accurately. Too fast learning rate simplifies that it will, the model that I'll be taking, that will be unstable. But if we are able to take it a perfect learning rate, then I'll get the best accuracy. Okay, so this is about hyperparameter. Now, what is hyperparameter tuning? Hyperparameter tuning means trying many settings and choosing the best one, like trial and error kind of method we are going up here. So here basically we are trying different learning rates, and I am at the end finding which learning rate is actually suiting the model, and based on that I am getting the best accuracy. Okay, so that is the thing. Now coming down how hyperparameter tuning actually works. Okay, so we'll get the steps. So first it will choose the hyperparameters to test. Okay, we have to choose, we need to choose the hyperparameter to test. Then we need to train the model for each choices that we have made. Okay, so coming down here, the choices being like how we can define these choices. So suppose we are discussing about learning rate. Okay, so I'll check learning rate for 0.01, 0.1, and 0.5. Like this would be my learning rate. So I'll check how it will work. And suppose epochs. So suppose I'll check epoch for 10, for 50, like how the accuracy or the model is performing based on this epoch of learning, right? So this is the choices that I made. So for each of the choices I need to train the model, and accordingly need to see how my model is performing. Okay. Next, the third step is to check the performance. And finally, we need to pick the best one. So this is about hyperparameter tuning. So types of hyperparameter tuning. So we have the manual tuning, we have the grid tuning, and we have the random search. Basically, tuning is manual tuning. Then we have the grid search, and we have the random search, and also we have the smart tuning. Okay, so we'll just discuss one by one. What is manual tuning? Manual tuning, like we'll try all of the value by hand. Uh, like we'll slow it down, we'll guess it. This is what we will be doing. Now, grid search means we'll try all of the combinations accordingly. So they like based on this, there are accordingly three tries. So it will be three trials we will be going. So based on that, we'll get the accurate result. Okay. Now we will be doing the random search. So we will be trying the random value so that we get the faster and often work like it often works well, the random search, because we try the random values. Okay. So this is all about the hyperparameter tuning. Now we will be taking which one is better, the grid search or the random search. Okay. First, just we have a quick reminder what we are searching. So we are searching for the best hyperparameters. For example, hyperparameters coming down for learning rate, number of neighbors, tree depth, number of epochs, this. Okay. So why do we need search? Because some settings work bad. Okay. They doesn't perform good. So some work okay and some work excellently, so we don't know the best one in advance. So we need to check the options, and based on that we need to find it accordingly. Okay, so what is this grade search? Grade search actually tries all possible combinations of values. Okay, so in real life, suppose I'm giving you the example, like I want the best ice cream. Okay, I want the best ice cream. I haven't given any options. Okay, so I have the flavors as for that shop. I have the option as like vanilla, chocolate, and the toppings I have nuts and the sprinkles. Like let me write it. Grade search. So what it does, it basically goes for all possible combinations. Okay, now let's check here. Basically, like grid search, I'll just take it a bit here so that we get the points closer. So now basically what are the options? So suppose we have flavors, that is vanilla. Then we have chocolate. Next we have the toppings, that is we have nuts and sprinkles. We have this details altogether. Okay. Now the basic thing is like grid search. What it will do, it will go for one by one. So we will be checking for all. So we have the flavor and the topping. Okay, sorry, FLAVOR, flavor, and we have the topping. Okay, so it will check with vanilla. It will be checking with vanilla with nuts. Next, it will check vanilla with sprinkles. Next, we have chocolate. So it will check with nuts, and chocolate, it will be checked with sprinkles. So these are all the possible options. Like, so it tries every single combination, and based on that, what tastes the best, it will give you, it will suggest you that. Okay. So grid search actually, this is of course a machine learning that that suppose we have taken the learning rate. For this, the learning rate we have taken as 0.01 and 0.1. Okay, so these are the learning rates we have taken. Okay, and we have taken the epochs as 10 and 50. Okay, so the grid search will do all of the combinations. It will take 0.01 with 10 epochs. It will take 0.01 with 50 epochs. It will take zero point 0.1 with 10 epochs, and it will take zero point 0.1 with 50 epochs. Okay, so this is how it will be taking. So it will take 2 cross 2, that is total tries would be 4. Okay, so how grid search works? We choose the hyperparameter. We make a grid of all of the values. Then we try every box in the grid and then train the model on for each. Okay, this is how my grid is formed. Okay, so we try every box in the grid and then we train the model on each of the grid that we have got, and then measure the performance. And finally, we pick the best one that comes under this. That is how this grid first search exactly works. So so the good things about grid search is it is very systematic and it finds the best result it gives when given it grids. Okay, and it is a very easy way of giving like measuring the performance. Okay, and the bad thing of it is of course it is slow and there are many parameters that we can consider over, and it will end up having too many combinations and it wastes time in some cases. Okay, so if you have suppose 5 hyperparameters, so 10 values for each, so total it will be 10 to the power 5, then it will be around 1 lakh models we need to prepare, right? So that is, of course, time consuming. Here comes the idea about random search. So random search tries a random combination instead of all. Okay. So random search actually like the same ice cream shop example, if you are taking, instead of trying everything, we randomly choose some combination, taste only those, and based on that, we give the result. So we have suppose tried like chocolate with nuts and vanilla with sprinkles. And based on that, we don't try all, we just take some of it and accordingly check. Suppose for all of it, for this result, we have all of this combination for grid search. For random search, we'll just take suppose this one and suppose this one. These two we will be checking randomly. Okay. So again, the same way the random search works, we choose the hyperparameter range, randomly pick the combination, we'll train the model, we'll measure the performance, repeat it for the fixed number of trials, and then pick the best result. Okay, so the good thing about random is that it is faster. It works well with many hyperparameters and find good solution quickly. And the bad thing is, as we are just going on the trial, like going on randomly basic, random wise picking it, in that case, we might miss the absolute based combination. So the result can change each time because of its randomness, right? So this is all about the random search. So we'll just give an overview of like differentiation wise overview. So we'll try all combination in case of a grid search, but in random search we don't try all combination. Speed is slower in case of grid search, but faster in random search. Best for small problem in case of grid search. The best for big problem, that is the random search. Okay, and efficient random search is more efficient, and there is more randomness that we can see in case of random search. So these are the details about hyperparameter tuning, grid search, and random search. Okay, so hopefully things are clear to you guys. So we'll connect in the next session accordingly, and we will be just going in details about like we'll just go in details with the how we need to train the models in case of unsupervised learning, how we can just what are the evaluation metrics. We'll discuss about elbow method, we'll discuss about fill out score, and we'll discuss about how to take it accordingly. Okay, so thank you guys for connecting in today's session. We will be connecting again in the next session and will complete the rest of the part of unsupervised learning. Okay, so thank you everyone. Bye guys.